Late at night when you plug your laptop in, do you ever stop to think about the invisible forces actually flowing through that cable? Welcome to this explainer. Today, we're going to take a really calm, step-by-step journey. We're going from the absolute tiniest atomic charges all the way up to the generation of the rotating magnetic fields that quite literally power our world. So grab a coffee, take a breath. No heavy textbook jargon today, no pressure. Just the fascinating reality behind the walls. We'll be breaking this down into 5 simple ideas. We're going to look at the invisible forces, power and energy fundamentals, the circuit players, the rules of the game, and finally, the phasor dimension. All right, let's start right at the beginning with our first idea, the invisible forces. So everything begins with charge. It's just the fundamental property of the tiny particles sitting inside a wire. Protons have a positive charge, electrons have a negative charge. In electrical networks, we measure this accumulated charge in a unit we call coulombs. Honestly, just think of a coulomb as our way of tallying up this gathered, invisible potential before it actually does any work. Now, when that charge actually starts moving, specifically transferring 1 coulomb per second, that's when we get electric current. You've probably seen that little equation I equals dq over dt. Well, it's really just an elegant mathematical way of asking, hey, exactly how much charge is moving right now? So if there's one absolutely crucial point to lock into your memory right now, it's simply this. Current is just charge in motion. Think of it like a quiet river. The water itself, that's the charge. But when that river starts flowing downstream, that actual flow is your current. And, this current can behave in 2 totally distinct ways. It can flow steadily in one single constant direction, which we call direct current, or DC, but it can also be cyclic. It can flow forward and then gracefully reverse backward, creating this continuous, beautiful sinusoidal wave. And that is your alternating current, or AC. Okay, moving on to our second idea, power and energy fundamentals. To get that river of charge moving in the first place, you need a push. In our world, we call this EMF, or electromotive force. Basically, it's the physical pressure behind the current that causes the electricity to flow smoothly through a conductor. Without EMF, the charge just sits there, completely peaceful and still. Once things are actually flowing, figuring out the rate of energy being delivered, the power, is beautifully simple. Power just equals voltage times current. You literally just multiply the push by the flow, and you get exactly how much work is being done per second, which we measure in watts. And that brings us to step 3, the circuit players. We can basically split the physical players in our networks into 2 main teams. First, you've got active elements, think voltage sources, that actively supply energy into the circuit. On the other side, we have passive elements. These guys don't supply any energy themselves, they just receive it, either to dissipate it as heat, like a resistor does, or to quietly store it for later, like an inductor or a capacitor. Another really helpful way to categorize these players is by how they react to voltage and current. Linear elements, like your standard resistors, act predictably. They follow basic rules like Ohm's law, meaning, hey, if you double the voltage, you double the current. Simple. But nonlinear elements, like diodes, they kind of play by their own rules. They might let current flow super easily in one direction, but then completely block it in the other. It's honestly fascinating to see how the theory bridges into reality here. We draw a simple symbol to represent a capacitor, right? But when you actually apply voltage to a real one, it doesn't just instantly fill up. The charge and voltage actually rise along these smooth mathematical curves over milliseconds, elegantly storing that energy over time. All right, on to idea number 4, rules of the game. All these physical players are bound by some pretty strict energy accounting rules. Take Kirchhoff's current law, or KCL, for instance. It basically dictates that whatever current enters a junction absolutely must equal to current that leaves it. There's no magic here, just a perfect natural balance. And while we track current with that simple balance, tracking the voltage uses Kirchhoff's voltage law, or KVL. It's essentially just adding up the voltage drops in a loop. You start at one point, gently walk your way around any closed circuit loop, add up the voltage drops across every single element, and then set that total sum to 0. It's nature's way of assuring us that the energy you start with always perfectly matches the energy you spend. And when you apply this logic to a real 2-loop circuit, it turns all this abstract theory into a totally solvable puzzle. By setting those voltage drops to 0 around each loop, you can calmly and predictably calculate the exact current flowing through every single branch. It just works. Which brings us to our final stop, Section 5, the phasor dimension. Now, when we shift over to alternating current, the math changes a bit. To solve these cyclic AC circuits efficiently, we reconstruct the sine waves using what's called a phasor. It's basically a vector rotating around a complex plane. The length is the wave's amplitude, and the angle delicately tracks the time. I know, it might sound a little abstract, but this math is actually a perfect mirror of what's physically happening. Because you see, this rotating dimension isn't just some neat math trick. It actually represents the physical generation of a rotating magnetic field. Think about it. Inside massive power plants all over the world, giant magnets are physically spinning. As they rotate, they push and pull those electrons we talked about earlier, generating a rotating magnetic field. And that physical rotation translates directly into the alternating current wave that travels quietly right into your dorm room or house. That spinning phasor on your paper, it's literally just tracking a massive spinning magnet in the real world. We started out today looking at invisible charges. We gave them a gentle push, we learned their accounting rules, and we saw how they spin into life. But just take a second and consider this. Right now, millions of spinning generators around the globe are perfectly synchronized. Their rotating magnetic fields are locked together in this delicate, mathematical dance to keep our entire grid alive. It really makes you wonder, what happens to the whole grid if just one of those massive spinning fields gently falls out of rhythm? It's a lot to think about. But for now, maybe just take a moment today to appreciate that quiet, invisible rotation that's powering your life. Thanks so much for exploring this with me.